Uh, Today we'll start the statistics part, but what we will talk today will not be part of exam 1.5. Right? Now, I hope the battery will last for, okay, it says 50% remaining, 1 hour 31 minutes, that's good. That's all we need. And I will post this one tomorrow. I'm not going to be able to post it today. Okay? I'll post it, I'll post sometime during the night. So what is the central limit theorem and what is the statistics part that we will do? We mentioned last time that when you have what we call population, this is a very general expression, and that intends to mean the following. It means that I have a random variable x. This random variable can be discrete or continuous. It's some random variable. And what I don't know is the parameters of its distribution, the parameters governing its distribution. So this is the main problem. Sometimes we may have an idea about the distribution, what type of distribution X might have, or we may have a very good idea about an approximate model of F. So we may know the distribution of X approximately, or the type of distribution of X approximately or accurately. Well, approximately or with, there is nothing accurate in science. There is nothing accurate. Okay, the accuracy is up to the accuracy of our measurements and of our ability to detect fine differences with our instruments. So to say that X has this distribution accurately, that's not correct. I can never prove that to mathematical precision. Everything works down to the precision of all of my instruments. So when I say X approximately, I mean allow some significant errors here. Or when I say or with very good approximation, that means for all practical purposes, this is an accurate model. But what I may not know is the parameters of this variable, of this distribution. And the parameters, unknown parameters, are usually the mean and the standard deviation. Typically, most distributions require you to know these two parameters. Or by getting the mean or the standard deviation, you may infer the parameters of the distribution that you know. So first moments, second order moments, first order and second order moments are what you need to know. And when you have multi distributions, then you need to know the covariance structure. Of course, that's more complicated. And in this course, we're not going to talk about that. That's an advanced statistical topic. So, when I say I know the population or I work on this population, I have defined the random variable, and I may have a good approximation about its model. And all I need to add from that point on are the parameters, the unknown parameters. This is called parametric statistics. So this is exactly the scenario of parametric statistics. We're not going to do non-parametric statistics in this course. We're only going to deal with parametric statistics. And the next thing that we want to do is, first of all, understand the mean, find the mean. So goal 1, find the mean. To find the mean is not the correct answer, is estimate the mean. That's all we can do, estimation. An estimation means approximate the value of the mean with some good accuracy. How good the accuracy can be? Well, you know, these days, now we all talk about the elections, and what you want to know is what the candidates want to know, those who work around the candidates want to know is the actual mean of their distribution. So let's see what elections would be. Elections are one type of very simple random variable. So here is an example, and let me just bring this further up so that you can all see. X is one random variable, 0 if you vote if you don't vote, let's say if you don't vote for Governor Romney, and 1 is if you vote for him. Why didn't I put 1 if you vote for President Obama? You can vote for a third party or something, okay? There are also other party candidates, independent candidates. A few, but there are some. So that's why, since I want to define correctly Bernoulli random variable, I would say 0 if you don't vote for Governor Romney, 1 if you vote for him. So he is interested in what actually is the mean of X. What type of random variable is X? It's a Bernoulli random variable. Why it's a Bernoulli random variable? Because you have either success or failure. So what is the parameter that governs this random variable? So what is important is to know the probability that X will be equal to 1, or other words, the PMF of X, the value of the PMF of X at 1. And I would call this simply with P, which is exactly the probability that someone votes for the government. A random voter votes for the government, for the governor. Correct? What is the mean of X? So this is, if I want to know the probability model of this random variable, I need to find P. What is the mean of X? It's a Bernoulli random variable. What's the mean of X? What? There's a little bit of confusion. If you even don't know the mean, how are you going to find the mean? It's an easy case. It's not rocket science.
It's the value of X multiplied by the probability.
By what probability?
By the probability of X whatever its value is.
So, what are the values here? 1 times what?
Times, so we have to find the probability of it.
No.
Times the probability of it.
What is the probability here? From what you see, P. 1 times P. I want the general model. Times 0. 0 times what? P minus 1 or 1 minus P?
1 minus 1.
Okay, because P minus 1 will be negative probability. So that's equal to P. You see that by knowing the mean of X, essentially you know what the value of P is. That's exactly what we will learn later on, not probably the week after. That's called the estimation of proportions. And exactly what you want to estimate is the value of P, and we will use confidence intervals to do these estimations. And for this particular case, we will use a confidence interval for proportion. For a proportion exactly is the proportion of the population that would vote for the governor. Okay? That's exactly his puzzling, the question that really is important to him and to his advisors. Now, he would like, what would the governor love? The governor would love to know exactly with three decimal digits accuracy, what is the percentage that he will receive in the elections, but this is not going very easily to happen. This is something that mathematically is very difficult. So if you see now the elections, the election polls, they didn't used to do that in the past, but now they are doing it a little bit more. I think the media are becoming somewhat more responsible in the way they actually present these results. Here, let's say, is the value of P, the true value of P. Let's call it P sub 0. Now, what will be reported from all the polls to the governor is a range of values within P sub 0. And an estimated value of P sub 0, actually his actual value, his true value of P will be within an interval. True value of P will be within this interval, which is centered at the value P sub 0, which is the value that is being reported to him. Value the Gallups, the polls give. Not the one that we do in the elections. If we go to the elections, then we do a census, because we ask the entire population of voters what they would vote, and they will they will express their disposition by casting their vote. So this is not the polls that are referring at right now are the statistical polls that basically they ask 1,000 or 2,000 voters of this kind or that kind, and it's a targeted population sometimes, and that's what they report. So what they give him right now, let's say 48%, I don't remember, 47%, something like that, is a value P sub 0. And then if you see the polls with very small letters, they report plus minus 3% sampling error. So that's exactly the accuracy, and essentially what it says is that if this P sub 0 is the value 47%, the true value of P, the true value of the proportion that he would love to know, and he's actually waiting until next Tuesday to find out what this value is going to be, should range between this number, which is the 47% minus the 3%, so that would be the 44%, and 47% plus 3%, which can be the 50%. So he can be anywhere close, anywhere in that. So that's an estimation, that's what we call estimation. And of course, the ideal situation is that we make this sampling error as small as we want, but that actually requires a lot of work. Primarily, it requires to get a bigger sample, a more representative sample. If your sample is not representative of the population, in other words, we will see exactly mathematically what that means, in reference, of course, to the central limit theorem. If your sample is not accurate, is not in the sense that it doesn't reflect the population, then you will lose. You will not get the value the sought value. You will get some estimation that doesn't have to do with reality. And that can happen for many reasons. Primarily because the sample the random sample that you have selected is not truly representative of the population. So statistics actually do the following. They take us what we call realizations of X. And what is a realization of X? X expresses your disposition, the disposition of a random voter to vote for the president or not, to vote for the governor or not to vote for the governor. So let's make an example of a realization. So let me ask my first friend here. So I'm asking him. First of all, are you a citizen? Yes or no? No. Can I ask his opinion about the governor? What do you think? I could. Then should I take into account his opinion? No, why not? Because he cannot vote. He's not a voter. So if I include him in my random sample, I'm corrupting the sample. I have to ask for somebody who is, actually, I have to ask for somebody who is a citizen and is a registered voter, is also eligible to vote, and is willing to vote. So I need three things. Willingness to vote, be registered to vote, and of course, if you're registered to vote, then automatically we assume that you are a citizen. Otherwise, you have fraud. So we're not getting into that part. So let's see. Do you have another registered? Do you have another registered voter? You are registered. Are you willing to vote? Yes. Now, when I ask her opinion, I'm not going to ask your opinion. What she will render an opinion. Yes, I will vote or I will not vote for Governor Roman. That her answer is the realization of the random variable text. Do you now understand what is a realization? I terminate the speculation and I see a fact. Now ask another person. What is your opinion? What are you willing to do? Vote for the governor or not vote for the governor? By person, I mean another registered voter who is also willing to vote. And I get a different opinion. That's another realization of the random variable. Realizations of the random variable are not exactly the same. What is exactly supposed to be the same, and what is exactly the same mathematically, is the percentage, is the disposition in which they will vote. So if I get all of the realizations in the census, when I do the census, when I do actually count the votes, P percentage of the votes will vote for governor only, and 1 minus P will not vote for P. I will only know the exact mathematical answer at the night of the election. Okay? Before that, I'm trying to estimate this number P by asking a smaller number of people. So, a random sample is using realizations of X. So a random sample, and that's the first important definition. A random sample is a set of variables, of random variables, x1, x2, x sub n, where all of them are, first, realizations of X, and this means that means the following: have the same distribution as X. Second, they are independent of one another. So it's very important when you when you take opinions, when you try to estimate P, to be able to ascertain that your random sample each time you ask, each time you conduct your poll, you are exactly within the group within the short group, the eligible, for my example, the eligible voters, and that your people, your random sample, each one of them represents the general population. Now, if I ask you, for example, if I take my random sample only from you, are you representative of the general population or not? No? Tell me one reason why not. One is geographic, correct? Yes. Age, that's another very important aspect. Education level, that's a third attribute that actually singles out. Perhaps income, yes. So all these factors, you already told me 4 factors that essentially puts you on what we call a stratum of the population. A stratum of the population is a layer of the population. So if you go to the online videos from last year, I have a lecture that I'm not going to present here, which says how to conduct sampling. If you watch the lecture, you're not going to understand all the aspects of sampling. There are people who work in statistics for many years, and they still see things that they haven't noticed before. They make mistakes when they try to sample, and they can only find out when their estimations do not prove correct. So they learn by trial and error. There's a lot of aspects here, but you will get some very general idea of how to obtain a random sample, which means how to guarantee the independence and how to guarantee that all of the random variable, all of your x events have the same distribution as x, are realizations of the unknown random variable. This is very important, which means they represent the general population in very simple words, in layman's language. If these two assumptions are not met, representation of the population and independence, then the sample is not random and anything that you will do is not going to work. It will work, you will give a result, but it will not be correct. Okay? So the central limit theorem, now let's talk a little bit about independence. If I ask you all, are you independent? How do I guarantee independence? When I go, first of all, and ask, oh, tell me your opinion, or tell me your opinion. Vocally, I don't, okay? Because if I ask the opinion of one person, the other person may be influenced to give the same opinion. Sometimes that actually happens. So when you ask opinions, you have to ask them by respecting the privacy of the individuals. Otherwise, people may influence their answers because they want to fit. In particular, we have observed the following, and I mentioned that in the video I'm asking you to watch. When you are person to person and you conduct polls that touch upon very sensitive issues like, sexual orientation or sexual habits or possible contamination from a disease, which actually relate to the habits of the individual, then it takes sometimes time to take out the right answer because people, first of all, feel ashamed, sometimes to reveal the truth. They are very shy. They get to feel more comfortable. They want to feel more comfortable with you. Or sometimes the way you may phrase the question may influence their answer and then they give you a response that you probably are actually waiting to receive. And that's one of the very big troubles. The way questions should be phrased should not motivate the individuals who participate in the poll to try to fit into your desired answer or your desired perception as you wanted to do the poll. That's why sometimes we have observed that on delicate studies, conducting the study on the computer, if you can guarantee that the individual will not enter multiple answers, are more desirable because you take out the person contact. So the individuals tend to be more honest when they type their answers to their computer because they don't feel the presence of another individual. They don't feel that they are being judged by rendering certain answers. Yes.
Isn't that like another thing of suggestive questioning? Like you suggest an answer in the question without actually...
Yes, that's exactly what I'm talking about. You should not, that's why I'm saying the question should be phrased with neutrality so that you don't suggest an answer.
Are you going to vote for Romney or are you going to vote for?
Yeah, that's a suggestion, but how else can you central limit theorem? So what is the central limit theorem? I would say it's the flagship theorem of a class of theorems which are called limit theorems. You've seen one limit theorem already. We did approximation of binomial probabilities with the Poisson distribution. That was one of the limit theorems. The central limit theorem has the following powerful conclusion. Suppose that x1, x2, x sub n is a random sample. From a population, so it means an underlying random variable, with, here's the big aspect, unknown distribution. So I do not need to know the distribution. It's distribution agnostic. Then a product random variable, which is called x bar, which is called sample average, and we've seen it last time. It's nothing else but adding the values of all the realizations and dividing them by n. This number n is called the sample size. Has approximately standard normal distribution with the following parameters. With mean, the mean of the random variable x, the mean of the population, and standard deviation, the standard deviation of the population divided by the square root of the sample size. Okay? So where the mean, these are the mean and the standard deviation of the population, of the sought population. Okay, let's go and look at a few things. I start from a population of whom I don't even have the finest clue of what its distribution is. And if I take the sample average, which is defined by this, I find that the sample average, as the sample size increases, That's why I'm saying approximately. I mean, as n tends to plus infinity, as you increase the sample size, has approximately normal distribution. Which what mean? The mean of the population and standard deviation, the standard deviation of the population, divided by the sample size. So you see that the mean has less variability. The sample mean has less variability because you divide, you don't keep the variability of the population, you divide, you get only a fraction of it. And the fraction can knock down this number a lot. So you more faithfully are going to get values very close to the mean. That's very important because this is the tool, the first tool that we use to estimate means. And we use it actually for several other ways. So the next thing I want to talk about is how to use the central limit theorem. Now, before illustrating the use of the central limit theorem, there's a difficulty. There's an inherent difficulty in the use of the central limit theorem. That difficulty relies on first giving out my pointer, and if that pointer decides to work, and does work, I'm saying n, as n gets to plus infinity, x bar becomes approximately normally distributed. That's the sample average, x bar. That approximation improves as n grows. But I do not know precisely what is the rate of improvement of this approximation as n grows. That's a general difficulty of all those so-called limit theorems.
What does that say in the
Approximately as n tends to plus infinity. Let me write it a bit better. It says as n tends to plus infinity. The smaller the sample size of the population, the less the accuracy. The bigger the sample size of the population, the bigger the accuracy is going to be. So, what I'm doing here is to show how we'll use that. Initially, I wanted to include this into the exam, but then I decided to leave it for the final, for exam number 2. Because it's more related to that. Let me show you some uses of it. Uses of the central limit theorem. I will call it CLT. And also I want to stress that I didn't give you the mathematically accurate the accurate statement. I gave you a statement that is good for practical purposes so that you can use it without being perplexed by the mathematical notation and rigor. So first use is to approximate binomial probabilities with the normal distribution. Actually, here I think I'm making a little bit of an error. That should be the 2. One should be approximate the probability of a sum of independent random variables, where x1, x2, xn are a random sample. Of x. And what I mean ix, the unknown random variable, or what I would call population in general. When I say sometimes the word, I use the term random sample, I also mean a set of random variables which are IID. What does IID mean? Independent, identically distributed. Identical. Yeah. And this is a term that comes very often in, appears very often in computer vision or in computer science in general. Signal processing, image processing, in all of those domains. Yes?
Could the random sample, could the results that you're getting, could they be similar to each other?
They can be similar to each other. Yes.
I've done this with, when we were doing titration in chemistry, and I've used this, that formula to find, basically we did titration like 100 times, and then we averaged them out. That's the same thing.
You got,
Not be
okay.
because they're from the same thing.
Okay, now let's resume and let's continue here. So when I have a random sample and I take the sum of the random variables, or when I have a sum of independent random variables, all from the same distribution, then I can use the central limit theorem to find the distribution of the sum. And what is this going to be? In this case, x1 plus x plus 2 plus x sub n is going to be distributed according to, it will be actually n times x, okay, x bar, okay? Because this is how I defined x bar. Let's see how I defined x bar here. Here is where I defined x bar. So the sum is n times x bar. If x has approximately normal distribution, then n times x has approximately normal distribution, correct? Because that's the multiple of it. Now, what is the approximate distribution of x bar? The approximate distribution is normal with the mean of x, and standard deviation, the standard deviation of x divided by the square root of n. So, what is going to be the mean of n times x bar? N times what? The mean of x, okay? So this is going to be n times the mean of x. Why? Because the E of x bar is approximately equal to the mean of x. And what is going to be the standard deviation of x, of the sum? So the variance, let's look at the variance of the sum first. What is the variance of the sum? Equal to, it's the variance of n times x bar. What is the variance of n times x bar? Taken outside of the variance is equal to what? N squared times the variance of x bar. And the variance of x bar is approximately equal to what? Sigma square, sigma sub x square, divided by the square root of n squared. So what is this going to give you? This is going to give you n times sigma x bar. So now you know the distribution. You know that this has approximately normal distribution. Sorry, this is the variance of the square root is this, all of this. And let me improve here. Let me elaborate here. Because what I calculated was the variance is this. So I know I can use this idea to find what is the approximate probabilistic model of a sum of independent random variables which all come from the same distribution. Now, when I do this, I can also approximate binomial probabilities. Why can I approximate binomial probabilities? Because binomial probabilities are, they come from the binomial. And what is the binomial? The binomial is the sum of the number of successful outcomes. Because I don't know why it died so precipitously, but anyway, I'm going to save now. Little stop. Established in item number one, to calculate binomial probability. So suppose that we have a function, we have a random variable y, which has a binomial distribution np. P is the probability of success in a single Bernoulli trial, so y has binomial distribution. The typical setting, the generic setting of the binomial of a binomially distributed random variable is that y is the number of successful outcomes in n Bernoulli trials, independent Bernoulli trials. And having said that, I can view these n independent Bernoulli trials as random variables, as actually a random sample from a Bernoulli distribution. It's with probability of success p. So this is exactly the n independent Bernoulli trials. Now, if one of these trials, if a trial is successful, then the random variable takes the value, the respective random variable from these x's takes the value 1, otherwise this takes the value 0. And therefore, if I add those, the zeros do not contribute anything to the sum, only the ones contribute to the sum, and actually the number of ones among these x1, x2, x sub n would give me precisely the number of successful outcomes in these n independent Bernoulli trials. So a Bernoulli a binomial distributed random variable can be viewed as the sum of n independent Bernoulli variables, all having the same probability for success, all having the same distribution. And now, if we use this to calculate what we have done so far, I can say that if n is big, we'll clarify later on what we mean by big, how big should be. If n is big, then the sum, that's what we established in one, has approximately normal distribution with what mean. Let's go back and see what the mean was, is n, the size of the sample, times the mean of the random variable, the underlying random variable. The underlying random variable here for each one of them is a Bernoulli with probability of success equal to p. So since x here in my case is a Bernoulli, then here we have also we calculated the variance in the sum, so that will become in terms of standard deviation, square root of n times standard deviation of x. So if x is Bernoulli, then the mean of x is equal to p. The standard deviation of x, let's calculate the standard deviation of x. Let's take the variance first. This is e to the x squared minus the mean of x squared. This is 0 squared times 1 minus p plus 1 squared times p minus p squared. So that will give me p times 1 minus p. So the standard deviation is going to be the square root of n times p times 1 of p times 1 minus p. So, in conclusion, y, which is the sum of these random variables, these Bernoulli random variables, which are all distributed with the same distribution as the Bernoulli random variable x, in other words, the probability of success per trial is equal to p, has approximately normal distribution with mean n times p and standard deviation equal to the square root of n times p times 1 minus p. And this is a very important result because it allows me, as n becomes bigger and bigger, this approximation improves. As n tends to plus infinity. And I can use now this trick to calculate binomial probabilities, and we can do that in the following way. Use this fact So we want to calculate now binomial probabilities, and again we have n experiments and p probability of success for each Bernoulli trial. Now, if I want to depict, or if I want essentially to show pictorially what is the probability mass function of this binomial, here is the graph, not in the usual calculus sense, but here is the graph or the pictorial representation of the PMF. And let's use again pictorial representation of PMF of Y. Of Y. And now this is called, here is a bar where you put all the probabilities actually of success, and I need also one, I need also for 0, so for 0 I need the value here, I need another bar, and you see for each realizable value of the random variable, I produce exactly at the value of the random variable a bar. The height of the bar is precisely equal to the probability that y will take the value k, which is exactly the value of the PMF of the random variable y at the point k, at the value k of the random variable. So this is the height, and this is called bar graph, because those probabilities are depicted with bars. So when we use an approximation of binomial probabilities using the normal distribution, what we do is that we essentially interpolate here a normal distribution graph. So essentially we will think that this axis goes all the way from negative infinity to infinity, and somewhere the range from 0 to n is here, and here we interpolate this, basically this bar. It should have landed line like this, So this is the graph. The green line here is the graph of the normal of an auxiliary random variable, graph of the PDF of the auxiliary random variable y tilde, where y tilde, this auxiliary random variable, has normal distribution, the normal distribution with the characteristics I wanted, mean n times p and standard deviation equal to n times p to the square root actually of the product n times p times 1 minus p. Now, when I want to calculate, to approximate this probability, what I do is that I create a bar. I thicken the bar. And I thicken the bar by basically going to k minus 0.5 up to k plus 0.5. And I draw parallel to the bar, I draw a rectangle. And here is the rectangle I draw. And this rectangle has height equal to the probability that y, so height of the rectangle is equal to the probability that y tilde will take values between k minus a half up to k plus a half. The length, the width of the rectangle's base is equal to 1, so the area of the rectangle, of the green rectangle, is equal, and this is the green rectangle, I mark it with green, the area, therefore, of this rectangle is equal to this probability. The fact that I subtract and add 1/2 is called continuity correction. And essentially is what we do, it's called continuity correction because I want to approximate the probability of a discrete random variable by using probabilities of a continuous random variable. Now, I couldn't do that by only considering the initial black bar at k, which is here, which lies in the middle of the rectangle. That wouldn't be possible because that bar graph occupies no area, occupies zero area on the two-dimensional plane. But if I thicken the bar a little bit, and that's what I do by going to k minus 0.5 up to k plus 0.5, so k is the center of this particular interval here, then what I have is that's exactly the continuity correction. I have now a rectangle which has area, and the area is equal to its height because its base has length 1, and I took the height to be equal to this probability. Therefore, the area of the rectangle will be approximately equal to the probability that the random variable y will take the value k, because k is very close to k minus 0.5, k plus 0.5, so this rectangle has exactly equal height has approximately equal height to the probability, to this particular probability. Or in other words, if I want to show that in the magnification, so if I want to show here the picture in the magnification, here what you would see would be. So the green line here is the graph of the PDF. It's in magnification, the picture that I have here. So the green line that I have here is the graph of the PDF of the normally distributed random variable y. Okay, so let's write it properly. That's what it is. The area under the graph, which is the green line, which I have here, goes all the way from here to here, and it's between the perpendiculars to the horizontal axis at k plus 0.5 and k minus 0.5, all this area that is now depicting with this green color is equal to the probability so green area equal to the probability that y takes the value between k and k plus 0.5. But since the range of the values is big, the range of the values, the n, which is the range of the value, determines what is the range of the value of the possible values of the discrete random variable is quite big. To go minus 0.5 and plus 0.5 of k does not really create a rectangle which is, does not create an area which is very different from this rectangle, the rectangle I originally have, and I will mark now with the red. And it's this rectangle here. This rectangle has height exactly equal, by how I constructed it, equal to the value of the probability mass function of y, which is the binomially distributed random variable, at k. So, since red rectangle, area of red rectangle is approximately equal to the area of the green area, and I mentioned before, and I'm repeating it, these two areas are approximately equal because k minus 0.5 or k plus 0.5 are not far from k relative to the fact that the range of the possible values of the discrete random variable y, which range from all the way from 0 to n. This is more clearly understood if you see it here. So the curvature of the graph of the normal distribution is not varying a lot relative to the upper side of the rectangle. You can see that here, so pretty much the two areas match with each other. The green with the area of the red rectangle. And therefore, we have this particular property, which is exactly the key of approximating binomial probabilities using normal probabilities from a normal distribution. So in other words, I have already made my approximation rule, the value of the binomially distributed random variable is approximately equal to the probability that y tilde, which has normal distribution, takes values between k minus 0.5 and k plus 0.5. And the fact that I add and subtract 0.5, this is called continuity correction. So, in general, if I want to calculate the probability that y will take values between k1 and k2, where these numbers are integer numbers, then what I do is that I take, and if these k1 and k2 are between 0 and n, what we do is that we take the probability that y tilde will take values between k1 minus 0.5, we take the lower bound and we subtract 0.5, and we take the upper bound of the interval and we add 0.5. And this is exactly the continuity correction, what we call continuity correction. When can we do this? This approximation be used. We need y to have binomial distribution, n be relatively big, which is, that's the rule for n big, that's what we call n big, n greater than 30, n times p and n times 1 minus p to be both greater than or equal than 10, and n times p and n times 1 minus p be of the same order. So in other words, if you divide n times p with n times 1 minus p, you should not get a fraction which is less than 1/10 or a ratio which is greater than 10. That's what we actually mean by the same order. The approximation is best when p is equal to 1/2, and it gets less good as p departs from this 1/2. If p is very small relative to 1 minus p, then we should not use that approximation, because for this approximation to be valid, it requires a truly much bigger n than 30. We should use the Poisson instead. So, before we use it, we have to check that y has binomial distribution. Then we option to use the approximation of binomial probabilities with a normal distribution. If n is sufficiently big, then we check these two numbers, and we also make sure that these numbers n times p and n times 1 minus p are of the same order. I will close this recording with one problem. So let's do one problem. I will do problem 1 from the book, page 225. So we have x bar here. We have the sample average to be the mean of a random sample of size n, equal to 48, and I hope that you still remember what is a random sample. If you don't remember, I can mention. So a random sample is a set of 48, a random sample of size 48 is a set of 48 independent random variables, all having the distribution having the same distribution and all of them having precisely the distribution of the underlying random variable. The problem is telling us that this is a random sample from the uniform distribution on the interval from 0 to 2. Therefore, all of them have uniform distribution on the interval from 0 to 2. Have exactly the same distribution. That's the uniform. It's specified by the problem. And this is always how it is being done. Approximate the probability that x bar will take values between 0.9 and 1.1. So we want to find when the sample average takes these values. Okay, now, of course, the easiest way to do it is to use the central limit theorem. Can we use the central limit theorem? We can use the central limit theorem because, so here is not exactly, is approximate, because we want to approximate this probability, and also because x1, x2, x48 is a random sample. The central limit theorem does not require us to have normal distribution. Okay, it's actually, the central limit theorem is distribution agnostic, but what it requires is that the sample size, which is 48, is greater than 30. That's what I meant. We have a random sample and it has the proper size, and that size is greater than 30. Actually, many authors would even say, and even your book would say, n greater than or equal than 15, because the uniform distribution is not skewed, which means it's symmetric, has PDF, has a graph, has a PDF whose graph is symmetric around where the center of symmetry is placed at the mean. What is the mean of the normal of the uniform distribution? Well, you can easily calculate that. So here we have x has uniform from 0 to 2. I expect you to do this calculation. X is the underlying random variable with a uniform distribution. I use this convention because I'm also using the convention x bar. And I use the uppercase X to denote my random sample. So what is the mathematical expectation of X, which is the mean of X? That's not very difficult to calculate. This is the integral from negative infinity to plus infinity of X times the density of X dx. But since the density of X is 0 if x is not in the interval from 0 to 2 and it's 1/2 if x is between 0 and 2, we have to integrate from 0 to 2 x divided by 2 times dx, which of course will give us x squared over 4 from 0 to 2, and this actually gives us 1/2, actually gives us 1. The middle of the interval from 0 to 2 is the mean. You can also state that. I decided to do it explicitly so that you have the example. Now, what else do I need to find? I need to find the standard deviation of x. So let me first find the variance of x. So I will take e of x squared minus the mean of x squared. Again, this integral will now be from negative infinity to plus infinity. I do second moment, x squared. I already calculated the mean, which is 1 to the square. So here I'm also going to do from 0 to 2 x squared divided by 2 dx, because this is 1/2 in the interval from 0 to 2, minus 1 square, which gives you 1. So here what I will have is, I will have x cubed divided by 6 from 0 to 2 minus 1. So that gives me 1/6. 8 minus 0 minus 1, so it's 8/6 minus 1, so it is 2/6, 1/3. So that's the standard, that's the variance. So the standard deviation of x is square root of the square root of 3 divided by 3. So now I can continue. I have what I need. What do I know now? I know by the central limit theorem that x has approximately, since the sample size is big, is greater than 30, it's 48, or greater than 15, because I don't have a very skewed distribution, it's very symmetric. Skewed means non-symmetric. X bar then will have approximately, let's put that approximately here, normal distribution with mean equal to the mean of the random variable x, and standard deviation, the standard deviation of the random variable x divided by the square root of n. And therefore this would be normal distribution with mean 1. Now let's put the standard deviation and the square root of 48. If we do the math here, then this will give us, in the denominator, this gives us 4 times 36, which gives us 2 times 6. So here this is, so x bar has approximately normal distribution with mean 1 and standard deviation 1/12, 1/12. So if I want to find now the probability that x bar has values between these, then the probability, sorry, that's x bar, that's bar here. The probability that is approximately equal to the probability that 0.9 minus the mean divided by 1/12, the standard deviation. And I use the fact that this has approximately normal distribution. So since x bar has approximately normal distribution, now I treat it as if it has normal distribution. So what I do is to switch to z. And how can I do this? By subtracting the mean and the standard deviation and divided by the standard deviation. So all this is set to z, and I assume that I pretend that z has now standard normal distribution. I take that as given, because x bar, in solving the problem, I work as if x bar has normal distribution, not approximate, as if it has normal distribution with this mean and this standard deviation. So I solve the problem now with normal distribution. That's what I do, and this is the typical procedure for solving a problem for normal distribution. So this is P. So the math gives me this, and therefore now I have that 1 negative 1.2 should be less than z, less than 1.2. And I go to the tables, and I find the difference, and this difference is going to be of 1.2 minus p of negative 1.2. So if I look at the tables on page, the page 568 and 569, negative 1.2 is 1.2 will be 0.8849. You do this and you find the problem. So that's our first problem here. We will close this recording with a little bit of with one remark. When we have a random sample, we want to find or approximate the values of certain parameters like the mean or the standard deviation, so we use other random variables from the random sample, and those random variables from the sample and we refer to these new random variables are called statistics. So x bar, which is the arithmetic mean of the sum of the random variables in the sum, let's do it here with n. So suppose that we have a random sum of size n. If we add the random variables of the sample x1, x2, x sub n, and we divide by n, this is called sample average, and it's a statistic. And it's the random variable that we will use actually next week to estimate the mean of x. So when it's used for estimation, estimator of the mean of x. So this is the concept of statistics. The final thing I want to add, we saw that the central limit theorem does not require us to have a priori knowledge of the distribution from which the sample comes. But it imposes, that comes with a price, it imposes some restrictions about the size of the sample, and the restriction about the size of the sample is that the size of the sample should be big. In contrast to this, if x1, x2, x sub n is a random sample from a normally distributed random variable x, let's say that this has normal distribution with mean me and standard deviation sigma, then for every n, regardless for any n, and I'm stressing this, any n, x sub 1 plus x sub 2 plus x sub n has normal distribution equal to the n times me, and standard deviation equal to the square root of n times sigma. And of course the mean has normal distribution, precisely normal distribution. These are precise distributions, not approximate distributions, because the original population is normally distributed. And for x bar, the normal distribution has mean equal to me, and standard deviation equal to sigma divided by the square root of n. And we will do some more problems using this particular fact next time in Thursday's lecture. That I think concludes this particular lecture. Thanks a lot for attending.